Okay, so I give you the reaction and I say, okay, what is this reaction's delta H? Now, so far we've only done one way to get H. So like if you know heat and you know moles, you could rearrange to get H. Okay, that's one way. So this next way, yep, I'm
You're
not
not
Scrooge, sorry. Okay, so we want to find the delta H for this overall reaction right here. Now, so far, the only way we've really been able to calculate H is if you had Q and moles. Okay, you could rearrange and solve for H. So this is going to be called Hess's law the long way. And what it means is that I give you a reaction and you don't know it's delta H. And I say, okay, I want you to manipulate this reaction and this reaction, meaning I want you to rearrange, move around, do whatever you have to do to get them to look exactly like this reaction. And once you do, you can combine their delta H's to get this guy's delta H. So this is called Hess's law the long way. So what does that entail? Well, okay, so what you're trying to do is you're trying to force these two reactions match this top one. So I have 2-ethanol. That's what this guy is right here. So if I look down, I have ethanol. It's right here. Here it is. So it's a reactant, and that's good because it's a reactant here. But the problem is that there's only one ethanol right here, and my overall reaction I'm trying to get to has 2. So how do I get 2? Well, I multiply everything by 2. So this will be a 2. 3 times 2 is 6. 2 times 2 is 4. 3 times 2 is 6. And then if you multiply everything there by 2, you also have to multiply the delta H by 2. Okay? Enthalpy is extensive, meaning if you have more stuff, you have more heat. Okay? So again, I multiplied by 2 to get it to match up here. 2 ethanols, now I have 2 ethanols. Fabulous. Now, strategy. The next substance we need to match is 1 oxygen. I need 1 oxygen as a reactant. I see oxygen in 2 locations right now, so I'm going to skip that until later. This is a strategy. Find the things you only have 1 of in 1 spot. So I'm going to skip the oxygens for now. We'll come back to it. So let's go to the product side. 2, and then this guy's name is acetaldehyde. 2-acetaldehyde, okay? So I need 2 of them, and they need to be on the product side. So I do see acetaldehyde right here, but the problem is the acetaldehyde is a reactant, and I need it to be a product. So I need to flip this backwards, which means everything that was a reactant is now a product, and everything that was a product is now a reactant. Oops, that's a 2. So my carbon dioxide and my water are now reactants, and my acetaldehyde and my oxygens are products. Now, remember I told you if this chemical reaction is exothermic, and how do we know it's exothermic? We know it's exothermic because the delta H is negative. It's literally the sign that tells you whether something is exo or endothermic. So if we know that this is exothermic one way, the opposite way, it's endothermic. So when we flip a chemical reaction backwards to get it to match, we also must flip the sign. So this is now positive 2385. If it's exothermic one way, it is endothermic the opposite way. Okay, now because I messed with this equation right here, I'm gonna get rid of it. I'm gonna just cross it off so that I don't have to look at it anymore because it's not useful to us anymore. We fixed it, we changed it, we manipulated it. Now don't get rid of the delta H, we still need that guy, okay? But I'm just gonna get rid of it so it doesn't confuse us, okay? So now I have taken care of the two acetaldehydes as products. So this guy's good now. And then I need 2 waters that are liquid. So let's look at our reaction and I go, okay, let's see. Well, I have 6 waters on the right-hand side of the arrow, the product side, and I have 4 on the left. Now, when we did redox, what did we say? Things on opposite sides are subtractive, right? So all 4 of these are gone. And 6 minus the number 4 is the number 2. Well, that works out nicely because how many waters do I have? I have 2 in my overall reaction. All right, so now let's look at our oxygens. Well, I have 6 oxygen as reactants and 5 oxygens as products. So all 5 of these are gone. And 6 minus the number 5 is the number 1, right? Oh, look, 1 oxygen right here. So I'm going to circle everything that we have. 2 ethanols are taken care of. 1 oxygen is taken care of. 2 waters are taken care of. 2 acetaldehydes are taken care of. And there is a little bit of an issue. I see carbon dioxide in both of these equations, and I don't see it in my overall reaction, which means we're going to cross our fingers that they cancel out. So do they? Well, we have 4 carbon dioxides on the left and 4 carbon dioxides on the right. So yes, they totally cancel out beautifully. So 4 on the left, 4 on the right. And now I have this, I've forced this to match. So what do? Well, you take this guy's delta H, the plus 2385 right here, and you add it to this guy's delta H, which is negative 1367 times 2. Take these two delta H's and combine them, add them together. So I'll give you a second to do that to see what you get. So this number plus this number. So we're adding them together. And we're doing that to try to get this guy's delta H. So again, this is just showing you when we multiplied it by 2, okay, or flipped and multiplied by 2. Okay, so this shows the 2 reactions. This shows them canceling out like I just did. All right, this is the overall reaction, and you should be getting negative 349. That should be your number. Negative 349. So what does that mean? It means that overall reaction is exothermic. How do I know? Because delta H is negative. And I did it doing what's called Hess's law the long way. I'm manipulating chemical reactions that we know their delta H's to, and then I'm adding them together. Any questions on how I got this negative 349 before we move on? We're going to do some more practice. All right, so here we go. So again, this is Hess's law the long way, where I give you a reaction right here, and I say, okay, what is this guy's delta H? I don't know it, so I'm going to take 2 different reactions, and I'm going to manipulate them to make them look like this reaction. Wow. And then I'll combine their delta H's. Sorry, I'm trying to make this better. Okay, so here we go. So you go, okay, 4 ammonias. So you look at your 2 equations down here where we do know their delta H's, and we find ammonia. It is not in this first one. It is in the second one. And the problem is I only have 2 of them. So what do I have to do? Well, I have to multiply everything by 2 so that I can get 4 ammonias. So if I multiply this by 2, now I can have 4. Which turns this into the number 6, which turns this into the number 8, and turns this into the number 6. And if I multiply all of the reaction, or all of the substances by 2, I also have to multiply the delta H by 2. Okay, ammonia is handled. I have it right here. Okay? All right, 3O2 is a reactant up here. And so I go to find O2, it's right here. This is the only spot it is. Now, there's 2 problems with it. 1, it's on the wrong side of the arrow. And 2, it doesn't have the right coefficient in front of it. So I need to reverse this. I'll do that first. So I'm going to put O2 plus 2N2 makes 2N2O. And if I reverse it, I have to reverse the sign. So instead of this being negative, this is now positive. Now I'm going to erase, I'm going to erase that first equation, so I don't have to look at it anymore because it'll just mix you up. So get rid of it, cross it out. Okay? So I flipped it, but I also have another issue. So now the oxygen is on the reactant side of the arrow, which is good, but I need 3 of them. So I need to multiply this equation by 3. So I also have to do that. So this comes out to be 3. This comes out to be 6. And this comes out to be 6 also. I'll do this. Now, you still have to multiply this by 3 also. Everything gets multiplied by the same. So I go, okay, I've now handled my 3 oxygens. Here they are. Okay, so let's keep going. I need 2 nitrogens. So you go, okay, let's look at my nitrogens. I have 6 nitrogens on the left and 8 on the right. Remember, things on opposite sides are subtractive, so all 6 of these would be gone. Okay, and what's 8 minus 6? That's going to be a what? A 2? Oh, that's going to work out nicely, right? 2. Oh, that's not looking good. 2, which is what we have right here. So I got 2 nitrogens. Awesome. Okay, what's next? 6 waters. Look at 6 waters right here. Sweet, it's already taken care of. Check. And then you go, what are these extra guys in here? These N2Os. Well, N2O is not in my overall reaction. So we're going to cross our fingers that they work out and cancel out. So look, 6 N2Os as reactants and 6 N2Os as products. They're on opposite sides, so they're subtractive. So I can cancel them out. Bye-bye. So now everything matches. So you take your delta H values and you add them together. So do your first delta H and add it to your second delta H. And I'm going to give you a second, but this is what you should get. So I'll give you a second to do that, please. Again, please, please, please plug in your calculators. There have been a lot of calculator issues today. So here's one last practice we're going to do together. Please don't let the fractions freak you out. This one is going to entail a little bit more work for this Hess's law the long way because there's 4 different reactions we're going to have to potentially manipulate. But don't let the fractions freak you out. I promise they'll work themselves out. So let's try this. Okay, we're using Hess's law the long way. How do I know? Well, I have the delta. I want to know the delta H for this reaction, and then I give you a bunch of delta H's for a bunch of different reactions. That's how you know it's called Hess's law the long way. So let's look. Okay, so I need 2 borons on the left. So I'm going to go and locate where my boron is. It's in that final equation. It's right here, and there's 2 of them, meaning it's like perfect. This is great. So having said that, you'll want to take this as a hint. You probably don't want to touch this reaction. Because if you do, you'll mess it up and then you won't have 2 borons. Like if you flip it, you won't have 2 borons. If you multiply it by number, you won't have 2 borons. So let's leave this bottom reaction alone. Okay? Now we're going to move on. 3 halves O2. I see O2 here. I see O2 here. I'm going to just ignore O2 for right now. That's a strategy. Ignore it. Come back to it later. Okay, B2O3 is a product. So I go, okay, where's my equation with B2O3? It's right here. It is not a product. So I know I for sure need to flip this. So let's flip. I like to write it out so I don't forget what I did. So now I'm going to flip. So I have 3O2 plus B2H6 makes B2O3 plus 3H2O, and I'm going to designate that this is water vapor because there's water vapor in here and water in the liquid form, which can be tricky. So in order to cancel stuff out, they have to be also in the same state of matter. Sorry. So now I'm going to cross off this. Right? I don't care about this anymore. I just changed it. I flipped it. Now, don't forget, if you flip the reaction, you have to flip the sign. So this is now not positive 2035. It is negative 2035. So this is negative 2035. And then you go, okay, well, I have B2O3 handled, right? That guy's good. Oh my gosh, there is so much stuff in here. Is that right? You go, oh, this is a disaster. Okay, there's all these waters and hydrogens and water liquid, water vapor. So here's the trick. I know that I had to flip this one, which means you're not going to touch this one again. If you touch it again, you'll undo what you did. So I'm not going to touch this one. Don't touch this again unless you need to like multiply. But you don't want to multiply, right? This is B2O3, this is B2O3. So I'm going to not touch this one and I'm not going to touch this one, which means I'm probably going to have to manipulate these two. So look at, I've got water in the gas form as a product. So I go find water in the gas form. Here it is. It is also a product. There is no way to fix this unless you flip this equation. So I have to get water on the opposite side as a gas. I already flipped this, so I can't touch it again. So the only way to do that is by flipping this one. So we're going to flip. So I'm going to do 2H2O gas going to 2H2O liquid. Okay, and then I'm going to cross off this top one so it doesn't confuse me. Okay, now if I flip that, I have to flip the sign, right? So this is no longer positive 88, it's negative 88. Okay, so now I have water vapor on opposite sides, which is great, but I now have water liquids on the same sides. Well, I just flipped this one, so I'm not going to flip it again, so I'll flip this next one. Flip. Oops, I didn't want it to be that size. Okay, so now we're going to have water in its liquid form, making H2 and 1/2 O2. Now if I flip this one, I also have to flip the sign. And then again, I'm going to go ahead and erase that equation above it so it doesn't confuse me. I just messed with it, so I'm going to get rid of it. Cross it off. Okay, so now I have liquid water on opposite sides. So let's kind of look at, there's multiple ways you can go about this now. There's multiple ways you can go about this now. The first thing I'm going to notice is instead of messing with the waters, I have been messing with them, I'm going to recognize that there are 3 H2 on the left here, and there's no H2 in this reaction. So if I have 3 H2 on the left, I'm going to need 3 H2 on the right to cancel. There's H2 on the right, which is great, but it's not the right number of H2s. So I have to multiply this whole thing by 3. So 3. Ugh, I didn't want that to be that big. 3/2, and then 3. Everything got multiplied by 3. Okay, so that will nicely cancel out my H2s. And then you go, okay, what else? What else is a problem? Well, the 3s and the 2s don't match. So like there's 3 liquid waters and there's 3 water vapors, but then there's 2 water vapors here and 2 water liquids here. So this is the tricky part. How do I get the waters to match? Does anybody have a suggestion of what you would which equation you would use and what would you multiply it by? And yes, you can use fractions. That's a hint. If you multiply this equation by 3/2, so this gets multiplied by 3/2. What's 3/2 times 2? 3. What's 3/2 times 2? 3. That works all of your waters canceling out nicely as 3s. Okay, so let's look at everything now. So let's look at the water. Oops, I'm going to do this. 3 water vapors on the left as gas, and then 3 water vapors on the right here as gas. Okay, cancel. 3 liquid waters right here, and 3 liquid waters right here on opposite sides, cancel. 3 hydrogens right here, and 3 hydrogens right here. Those cancel too. Look, we don't have any, we don't have any hydrogen up here. Oh, there's another guy, B2H6 on the left, B2H6 on the right. Great, they cancel. So now we have our boron, our diboron trioxide, and then now we have to work out the oxygens. So because this guy is in a fraction, I'm going to rewrite 3O2 as a fraction instead. So over 2, what number do you put over 2 to get the number 3? Oops, sorry. Oh, jeez. 6 halves over 2 is the same thing as 3O2. These are the same thing. I'm writing it as a fraction because these guys are on opposite sides and we're going to have to subtract them from one another, right? Because they're on opposite sides. So it's just easier to work out the math. So 6 halves O2 minus the 3 halves that are right here leaves me with 3 halves O2. So this works out beautifully. So now we take negative 2035 plus negative 88 times 3 halves plus 286 times 3 plus 36, and you should get this number. I'm going to give you a second to please calculate it on your own. Okay, so Hess's law, the shortcut method, involves what are known as enthalpy of formation values. Enthalpy of formation values. That's what this little F stands for. And by definition, a formation value is the number associated with forming 1 mole of a compound from its elements. So, sorry, I gotta plug my laptop in. Otherwise, the battery's gonna die. Okay, so the enthalpy of formation of a compound, so any compounds have formation values. So at the so they call this standard enthalpy of formations, and you go, well, where do these numbers come from? So most of the time when we do problems like this, you're going to get these numbers from a chart or from the book, okay? So instead of calculating delta H using a bunch of different reactions and their delta H's, which is what we were doing, we're going to use what are known as enthalpies of formation. So let's talk a little bit more about what formation means. If you look at this formation, this is the formation of magnesium oxide from its elements. Now, the elements that make up magnesium oxide are magnesium, and then under standard conditions, oxygen's diatomic. Now, before, when we were balancing, right, you would put like a 2 here and a 2 here, which isn't wrong, but it is wrong for a formation equation. By definition, you are only allowed to form 1 mole of the substance from its elements. So there can't be more than 1 of these right here for a formation value. So that would force us to put a half here, because a half times 2 gives us 1 oxygen. So a magnesium and a half an oxygen make 1 magnesium oxide compound, and it has a value associated with it. So this is what it's saying, is this much energy is released during the formation of magnesium oxide. And now this isn't always true, but it is a majority of the time true. The formation of compounds is generally exothermic. Most compounds release energy when new bonds are formed. So breaking bonds is endothermic. You got to put energy in to rip them apart. But the formation of new bonds is exothermic. That energy gets released when the compound is formed to achieve more stability. Now, not every single formation is negative, but a lot, like a lot of them are, okay? So let's try just doing some formation equations. I'm going to do the first one and then you're going to do the second one. So we're going to just write out formation equations for different compounds. So the first compound is going to be, this guy's called methyl bromide. It's an organic compound. So you go, okay, well, what elements make up methyl bromide? So carbon is one. It's not a diatomic. Hydrogen is another one. It is a diatomic. And bromine is another one, and it is a diatomic. So these three elements combine to form 1 mole of methyl bromide. So you go, okay, so one carbon. 3 hydrogens, yuck. So you've got to put 3 halves here. 3 halves times 2 is 3. 1 bromine. So you have to do this. 1/2 times 2 is 1, right? Because we're only allowed to form 1 mole of the product. That's by definition what formation equations are. You're making just one of the compound. So now I want to give you a second. I'd like you to try to do an enthalpy of formation of sodium nitrate. So we're going to form sodium nitrate, and I'll give you a second to do that. Okay, I see this happen a lot on these because you recognize that this is an ionic compound. And this is the formation of sodium nitrate from its ions, but that's not what formation equations are. Formation equations are the formation of a compound, whether it's ionic or molecular, doesn't matter, from its elements. So we can only use elements in here. So sodium is one of them, and it's a metal, so I just leave it like that. Nitrogen is one of our diatomics, so I write it as N2, and so is oxygen. Okay? So then this would be 1/2 N2, because 1/2 times 2 is 1 nitrogen. And then this is an ugly 3 halves times 2, because that will give me 3 oxygens. This is the formation of 1 mole of a compound from its elements. Any questions? All right, let's keep going. So this is called Hess's law, the shortcut method, because really for this, you're just plugging and chugging in numbers. Meaning, like if you have 4 variables, you have 3 of the 4 and you solve for the 4th. So they call it shortcut because it takes less work, really. So mathematically, the delta H of the reaction now is going to be solved by plugging in enthalpy of formation values. And where do these values come from? Like these will come from like a chart, okay? You'll have to like look them up. They'll be given, okay? So we're going to calculate the delta H this way. Now, remember Hess's law the long way, we calculated delta H using a bunch of different chemical reactions who we knew their delta H's and we manipulated them. That was one way. So this is a different way. Now, this little sigma represents sum, okay? So it's going to be the sum of all of the values for the products minus the sum of all of the values for the reactants. Remember, this delta means final minus initial, right? So products are our final and reactants are our initial. And then again, this little circle here just means it's under standard conditions, aka 1 atmosphere, 25 Celsius. And then there's one thing you do need to know. HF values for any element are 0. Anything pure elemental, anything is 0. And then you go, well, why? Well, by definition, a formation value, it means you're forming a compound from its elements. So an element can't have a formation value because an element isn't a compound, it's an element. So there's no formation values for elements. The formation values are for what energy is associated with forming a compound, not an element. You're forming a compound from its elements. So HF values for elements are always 0. So how does this work? You go, okay, using standard enthalpies of formation, so these are H is enthalpy, F is formation values, calculate the delta H, so this is now how we're going to calculate delta H for the following reaction. And I give you a balanced chemical reaction, and then you'll notice I give you H of formation values. So you go, okay, well, delta H of a reaction is going to equal our products, all of our products added together, minus all of our reactants values added together. And you do have to consider coefficients, Okay, you do have to consider coefficients. Remember, enthalpy changes when there is more or less stuff, so coefficients will matter. So products, okay, so these guys are my products, aluminum oxide and iron. All right, so let's do products. So here we go, products. My aluminum oxide is -1676. Plus, I have another product, so my products are added together. Now, this is 2 times, what's iron's enthalpy of formation? 0. Why? It's a pure element. Okay, it's expected that you know that. So products minus reactants. So my reactants are 2 times aluminum, which is 0 because it's a pure element, plus iron 3 oxide. I'm given it right here. Here's its enthalpy of formation, -826. So calculate this out. I do need you to be practicing in your calculators. 2 times 0 is 0. 2 times 0 is 0. So calculate this out. It's -1676 minus -826, and you should get -850. So the delta H for this overall reaction using enthalpies of formation is -850 kilojoules per mole, meaning this reaction is exothermic. This much energy is released, lost, given off, produced. Any questions on that calculation? So they call it the shortcut way, right? Because this is not even close to as much work as Hess's law the long way. So how do you know which one you're supposed to use? Well, you know which one you're supposed to use given by like what data you have, right? Hess's law the long way, I would give you this reaction, I'd ask for its delta H, and then I would give you a bunch of other reactions to manipulate. I didn't give you that here. I gave you enthalpy of formation values for these guys, and we know these guys are 0. So now we're just going to plug into products minus reactants. So it's up to you to recognize what's given and how you use it. Okay, let's try another one. All right, using standard enthalpies of formation, so HF values, calculate the standard enthalpy change of the reaction. So we're calculating delta H for this whole reaction. And I give it to you balanced. So our job is to find the delta H of this reaction using HF values, not using chemical reactions with H values. So you go, okay, well, if I'm using HF values, this is defined as products minus reactants. Delta H equals products minus reactants. So I'm going to do this. Delta H of the reaction is my products, the sum of all of my products, minus the sum of all of my reactants. Products minus reactants. Okay, so now I'm going to go back here, and I'm going to have to look at my coefficient. So it's 4 nitrogen dioxides and 6 waters for products. So 4 times 33.84. So this equals 4 times 33.84 plus I have another product, waters, 6 of them, 6 waters right here, and it's -285.83. Oops. So products minus, so this is products, minus, now I got to go to my reactants. So I have 4 ammonia, and ammonia is -46.19. And then plus I have 7 oxygens. Well, oxygen is pure elemental. It's just O2. So its value is also 0. Okay. So take a second and calculate this out. I'll give you a second to calculate it. So this whole number minus this whole number. 7 times 0 is 0, so you can just get rid of this. Doesn't matter. Okay. I'm going to give you a second to please practice with your calculator. I had numbers all over the place last class. Oh, sorry, the units are kilojoules per mole, meaning this reaction is exothermic, and this is how much energy is released. How do I know it's exothermic? Because the sign is negative. That means this much heat is, that minus means lost, given off, produced, released, exothermic. All right. So now we're going to try something a little bit different. So we're going to calculate an enthalpy of formation value. So in the last couple of problems, we calculated delta H of the overall reaction using formation values. Now I'm going to give you the delta H of the reaction, and I'm going to ask you to calculate the formation of one of the substances. So I gave you the delta H of the reaction, so I'm asking you to find something else. So look at, if we set up the equation, remember, delta H of the reaction is products minus reactants. So I'm actually given this time, which is what I was solving for the last time. So now I have a number here, which means I could find one of these numbers over here. So let's plug in what we know. We know that the enthalpy change for the reaction is 178.1 kilojoules per mole. So this number is 178.1. That's my enthalpy of my reaction, equals. So it's my products minus reactants. So let's go look back at that reaction. Who's my products? Calcium oxide and carbon dioxide. This is all balanced. Everything is 1 to 1 to 1. Okay, so we're not going to have to really worry about coefficients. So calcium oxide product is negative 635.5. Plus, what's the other one? 393.5, because that's carbon dioxide is my other product. Is it 393? So products minus, and then reactant, I only have one reactant in here, right? It's calcium carbonate. That's who you're trying to find. You're trying to find this guy's HF value. Okay. Is it, oh, is this guy negative? Did I miss this? Is this negative 393.5? Let me go back. Yeah, sorry. I forgot the negative out in front of it. Thank you. Okay. So add these two numbers. And then now we have to move whatever this is to the other side. It has to come over here. So this is just basic algebra. Now be careful because that's going to leave you with negative, right? This is minus calcium carbonate. So then you also have to move the negative sign over there too. So if you take negative 635.5 minus 393.5, does anybody have that number? This number right here, the 635 and the 393 together? It's negative what? $1029. Okay, negative 1029. So how do we get rid of it? We would add 1029 to both sides. So what do we get over here? So 178 plus 1029 is what? Something 0.1. $1207.1. But remember, this is minus calcium carbonate, so that minus is still here, so I need to move this over. So calcium carbonate's enthalpy of formation value is negative 1207.1. Because remember, it's products minus reactants, so that minus has to get moved over here. Any questions on that? So again, it's just a different rearrangement. All right, let's try another one. This is an FRQ from 1984. Oh my goodness, way before you were born. It actually was the year after I was born, so I was very, very little. So if you read this, it says the enthalpy change for the combustion of butyric acid is, and I give you its number, kilojoules per mole. So look at enthalpy of combustion. They could have just as easily called this the enthalpy of the reaction, and it doesn't matter. These things mean the same thing. The reason they wrote combustion is because it's specifically a combustion reaction. So they give it to you and they balance. Now, who remembers what but means? Anybody remember how many carbons but means? Meth, eth, prop, but. It's 4. And you go, well, that's not 4. Well, yes, it is. Look at this is 3 carbons here, and then there's the extra carbon, 4 carbons. Okay. So again, they call this butyric acid. And then it says from the data above, so that's this data table right here, calculate the enthalpy of formation. So this is just like we did in the last problem for butyric acid. And the reason that I can do this is because they gave me the enthalpy of the reaction right here. So if you look at this chart, you see this D. That D stands for delta. And remember, delta just means triangle. So they're literally saying triangle H, okay? Now, absolute entropy, you don't know yet. That's the second part of thermodynamics that we're not doing right now. So right now, for the sake of this problem, this means nothing to us for now. It will second semester, just not right now. Okay? So how do you do this? Well, remember, delta H, and this is of combustion, equals products minus reactants. And then this number is given. So this number is negative 2183.5. Equals, so products, my products are carbon dioxide and water because it's a combustion reaction. So 4 carbon dioxides and 4 waters. So you go up to this chart where they give you a bunch of enthalpy of formations. So 4 carbon dioxide, so it's 4 times negative 393.5. Plus, I have another product. It's water, 4 waters. And they called water negative 285.85. So products. Minus reactants. So let's see. I've got butyric acid. That's the guy I'm trying to find. That's like your X. Oops, sorry about that. So this is this guy's enthalpy of formation, right? Reactant. So this is this, and then it's oxygen, right? I don't remember. Was it 5 or 7? 5. 5 oxygens. So that's 5 times, but oxygen is just elemental, so that's 0. So again, 5 times 0 is 0, so we can just ignore this guy. So rearrange. Calculate this entire top number, move it over here, okay? And then you're going to end up with, again, an opposite of the HF value of butyric acid. So then you'll have to move the negative sign over, whatever this math comes out to be. So this times this, plus this times this, and then you subtract that from both sides. or add the negative, whatever it is. So, oh wait, I'll let you guys calculate it out. Again, please be practicing in your calculators. So again, negative 533.9, or the opposite side came over, kilojoules per mole. And then again, Martin had asked if there was a 2 in front of this. Yes, you would have to, whenever you get this number, then you would have had to have divided it by 2, okay, to isolate the butyric acid by itself. All right, great job. So you just did part of an FRQ. Let's do the next part. It says, write the correctly balanced equation for the formation of butyric acid from its elements. Okay, that's not too difficult. So we're going to form butyric acid from its elements. Well, so we're forming C3H. Oh, I'm going to run out of room. So we're forming C3H7COOH from its elements. So we've got carbon involved. Hydrogen's a diatomic, right? And so we have to write H2. Sorry, that kind of looks funny. And oxygen's a diatomic, so we have to write O2. So 3 carbons plus 1 more carbon is 4 carbons. There are 7 plus 1 more, there's 8 hydrogens, so 4 times 2 is 8, and 2 oxygens. Oh, this one's nice. This one doesn't have fractions. So this is the formation of a compound from its elements. And this has a number. The delta H of formation we just calculated was negative 533.9. That's what would have gone right here. Okay, that's its enthalpy of formation, meaning when you form butyric acid from its elements, this much energy is released. Any questions? Enthalpy of formation is just the values are what the formation values are that you can combine in an overall reaction to get the delta H for the overall reaction if you want it. But enthalpy of formation values are just the amount of energy associated with the formation of a compound from its elements. So if you took 4 carbons and 4 hydrogens and O2 and smashed them together to make butyric acid, this much energy would be released in the formation of butyric acid. HF values are how much energy is associated with forming a compound from its elements. And if you know all of the values, their HF values, which you would like look up in a chart, you can calculate the H of the reaction doing this like shortcut method, which is what we're doing. It's like an alternate way. Okay, so last FRQ. And then we are finished. So 1995, you guys still are definitely not born. Okay, so we've got propane. It's used for cooking, right? Propane, like if you want to barbecue, that's what you use. We're going to write a balanced equation for the complete combustion of propane. Okay, you can do that. Write a balanced reaction for propane blowing up. Shouldn't be too hard. Combustion means you add O2. So this is a 3, this is a 4, this is a 5. Okay, so we just did A. Sweet, you got some points just on the FRQ. All right, the next question says, the heat of combustion of propane is this number. So this is delta H of combustion. Calculate the enthalpy of formation or heat of formation of propane, and then they give you a couple other enthalpies of formation. So this is just like the last problem. So, oops. The delta H of the whole reaction is your products added together minus your reactants added together. How do I know I do it this way? Well, because I'm given HF values. Also, when we did Hess's law the long way, They give you a bunch of chemical reactions below it. I don't see that anywhere here. Okay, I just see HF values. So let's plug in. So this is negative 2220.1 equals, so this was given. So products, so 3 times carbon dioxide's HF value. What is that? Negative 393.5. Plus 4 waters, 4 times negative 285.3, I think is what they have for the HF of water. So these are my products minus reactants. So propane is the one I'm trying to find its HF value. So I don't know propane. It's like your X. So minus, let's do a different color. So we're doing propane, C3H8. I want this guy's HF value. Plus 5 oxygens. But oxygen is pure oxygen. It's elemental, so its HF value is 0. Okay, so you can pretty much cross this off. All right, rearrange, put this on the other side, and then you'll end up with negative enthalpy of formation, so you have to move the negative over. I'll wait for an answer. Molar mass of propane is 44.1, so that will get me my moles. So remember the minus goes out front. What's my moles? What does that come out to be? I know the bell rung, but just bear with me for those of you that are still on here. What does that come out to be? Is this 0.76 something? No, I don't remember from last class. 30 divided by 44.1. 0.68-ish moles. Okay, what's the enthalpy of combustion? Well, the enthalpy of combustion was given in the problem, but the issue it's in kilojoules per mole. So I'm going to change it to joules per mole. So 0.2220, and then it's 0.1 kilojoules per mole. So negative 2220.1, right? And then you got to go over 3 spots to turn it to joules. 1, 0, 0. That's joules per mole. Okay. So there's the N, there's the H. What's the mass of the water? Well, they gave you the mass of water in kilograms. 8 kilograms is the same as 8,000 grams. Again, I'm converting these because your specific heat constant is 4.18 joules per gram Kelvin. They give joules and they give gram. This doesn't say kilojoules and this doesn't say kilograms, so that's why I converted it. So look at your grams cancel. Your joules cancel, your moles cancel, and you're left with Kelvin. Now remember, you have to take whatever this number is, the opposite. So this whole number right here, this whole part right here, should come out to be negative because of this guy. So a negative and a negative makes it a positive. So it's delta T ends up being 45.1 degrees Celsius. That's how much the water changes or heats up by, or 45.1 Kelvin. Remember, delta T can be in Celsius or Kelvin. All right, so that is where I'm ending today. I need to, once you guys log off, I'm going to go back and try to re-record this. Otherwise, I will see you Friday, and we will finish notes on Friday. Have a good day. All right, so we're gonna take and assume that all of the heat given off from combusting this propane, specifically we're gonna combust 30 grams of propane, is completely transferred to water. So the heat lost by the propane is the heat absorbed by the water, okay? So what does that mean? So we've actually talked about this earlier in this chapter. So we'll do the propane reaction like this. Enthalpy or heat, I'm sorry, heat of combustion of the combustion reaction. So the combustion reaction is losing heat. Remember, heat is Q. And the water, I'll do in a different color, is gaining the heat. So now you have to decide, well, which equations am I going to plug in for Q? Well, the water, if it's going to heat up, is liquid water is definitely going to change temperature. So we're going to use MCAT, MC delta T of the water, okay? That's Q for the water. Now, Q for combustion, the combustion reaction during it, nobody mentions anything about temperature change. So the only other equation we have for Q that doesn't involve temperature change is NH. So this is NH combustion. Now remember that negative sign still has to go out in front, right? Q equals NH and Q equals MCAT. So earlier in this unit, we had two MCATs that we set up equal to each other because both substances were changing temperature. Now in this case, the combustion reaction blows up and the water takes in the heat, okay? So there's no MCAT over here, it's NH. And then you go, okay, well, what did they ask for? They asked for what is the increase in temperature. Obviously, you know if this is going to release heat, the water's going to heat up. So it's an increase in temperature. Increase in temperature is delta T, change in temperature. Okay, so to isolate it by itself, you just move both of these terms over here. Okay, that gets rid of this over here. Now I need to make this bigger. Now, there's kind of an issue with this. This is plug and chug. However, there's lots of funky units. You should notice that the specific heat for liquid water is 4.18 joules per gram Celsius or joules per gram Kelvin. So they have joules and they have grams, which means you need to change your enthalpy from kilojoules to joules and you need to change your mass from kilograms to grams. So the first thing we're going to do is find moles. So you go, well, who do I find the moles of? Well, this equation belonged to the heat of combustion, and it's the propane that is responsible for combustion. And you're burning 30 grams of it, and it's 44.1 grams per mole. That's its molar mass. So that's how you'll get the moles of propane. And I think that comes out to be, so I'm going to put that minus here again, and then I'm going to do this. Okay, I'm leaving this, right? This is that negative opposite because the combustion reaction is losing heat. So the moles is 0.68 moles. And then now, I'm going to kind of get rid of this for just a second. I'll put it bigger. Okay, so now, so there's N. So enthalpy of combustion. So if you go to the enthalpy of combustion, you look it up, the number is negative 2220.1 kilojoules per mole. Well, the C constant right here is in joules. So I'm going to change this to joules, meaning I'm going to multiply by 1,000. So this is going to be, so N times H, so negative 2220.123. I moved my decimal spot 3 over. Now this is joules per mole. That's H of combustion. Divided by the mass of the water. So they gave you 8 kilograms, which is the same as 8,000 grams. And then, so that's M of the water. And then specific heat of liquid water is 4.18, and they gave you joules per gram Kelvin. So look at the units. Your grams cancel, your moles cancel, your joules cancel, and you're left with Kelvin. And here you go. Look at this negative right here, and look at this negative right here. They will cancel each other out, and delta T ends up being 45.1 Kelvin, or you could rewrite it as 45.1 degrees Celsius. Remember that that Celsius and Kelvin for delta T are interchangeable. So again, the water would heat up 45.1 degrees. It would increase by that much temperature change from combusting 30 grams of propane, assuming a perfect transfer, like that none of it's lost to the container, none of it's lost to the room. We're assuming like this perfect thermal transfer. Okay, so this ties a lot of the concepts from this whole chapter in all in one spot.